Yeah. Sorry. Yeah, I think that. Yeah. Fair enough. Yeah.
Oh, that's right. That's like,
Yeah. Right.
He's sitting right next to you to make sure that's happening. Yeah.
Scary.
No, but I was like, and we somehow end up talking about everybody hires
So what's the name of that session?
Meta workshop.
What is the name? But it says in the schedule, it says knowledge graphs. This one, right? Okay. Ah.
Yeah, I think it's.
Okay. Whatever we call it.
This one. Yeah.
I will figure it.
Yeah.
Yeah, no, I said.
Let me go with this. So I already I know. Yeah, it's great.
if you have questions, let me know when I bring the microphone to you, okay?
Yes. Can you hear me? Yeah.
It's up.
Check, check. All right, guys, I think we're ready to go. So this is a repeat of last year. It was so good. We're bringing it back. Come on in. You can sit in the back, sit anywhere. I'll try getting some chairs for you guys. We're very lucky to have Nico as well as Vijay back for round 2. If you have questions, just raise your hand. They'll select you. There's mics in the room, so just say your question really, really loud, and the speakers will repeat it. So without further ado, to make sure I don't take too much time, I'm going to pass it on to our speakers.
Awesome. Are we good? Oh, the clicker. Great. Thank you so much. Excellent. All right. It's our great pleasure to be back to talk to you about a topic we spoke about a year ago. This is knowledge graphs and large, massive language models. We do think it's the future of AI. I think this is what we said a year ago. Where do I point this to? I don't want to point in someone's eyes. Here, is this better? Not really. You good? Right. So I'll keep speaking while we get this set up. Right. So we still believe it's the future of AI. We are this combination. We are now from different ways of counting about 4 years into this new era. I'm counting from the beginning of when GPT-3 came out, or a year into it, if you look at when GPT-4 came out around March of last year. I think it's really a whole lot of commercial interest got spawned about a year ago. So we are a year into it. There are a lot of learnings from this time. I should perhaps give you a little bit of introduction about who I am and what I'm doing, and hopefully Nico will soon get a chance to do the same thing. So I'm Vijay Saraswat. I am currently head of Gen AI at Fidelity Asset Management. I joined almost a year ago, and I'm also founder of Gen AI startup in the sports and entertainment space. In fact, I'll be talking a little bit about all of the sports and entertainment stuff as we go along during our talk. So mainly what we have been doing for the last year or so is trying to get real applications out in the field using primarily GPT-4 class machines. And there are a lot of lessons. I guess I would summarize it today, just to get you started off on this, by this is, of course, the most amazing technology, large language models, Gen AI, that we have seen in my lifetime in computer science. I've been an active computer scientist for over 4 decades at this point, but it is also extremely frustrating. It's also something that's very difficult to work with when your goal is to solve your customers' problems and get a product out in the field that they can use reliably. So the main purpose of our talk today is to walk you through some of the practical issues that we have been encountering in our journey to get real products out there, but also acknowledging that, in fact, it has been a year of amazing progress in this space. There are a whole ton of new ideas that have come out, things that have just come out within the last month or so, particularly with respect to using so-called multi-shot prompting with one million word, 1 million token context of Gemini 1.5 Pro that are pointing to some potentially very powerful ways of doing the stuff that we have hitherto been doing with GPT-4 with 128K tokens and so on and so forth. Okay, do we think we are going? Oh, I see. So that's not going to work. All right, let's get going on the next. We are doing this. So Nico, why don't you take a minute to introduce yourself? I just introduced myself.
One? Yes. Hi, I'm Nick Vasiloglou, VP of Research ML at relationalAI. We are in the relational knowledge graph space. And, as you understand, language models and knowledge graphs go together. So this is the team of people that work for this presentation. We've been experimenting a lot with reasoning and knowledge graphs and GenAI together. So I will just keep it quick.
So here's what we are going to do. We are going to cover a little bit of stage setting, some of the things that we did last time, revisited a year later. And then we are going to get into a bunch of new things that have happened. We go on to the next slide. Bunch of new things that have happened since that space. And we will focus on a few major ones, primarily the one about multi-shot prompting, and then about self-discovery as a certain framework for developing sophisticated LLM-based programs. And in the meantime, we also have a whole bunch of other things besides these two that have to do with integrating with symbolic computing, integrating with solvers. It's really, this should not be a surprise. We feel that it's the combination of the real-world knowledge, the linguistic competence of LLMs, plus the formalized representations that traditional constraint solvers have been very good at. It's that combination that makes for a really powerful set of tools to work with. So this is what we talked about a year ago, to lay the stage for what has happened. And pretty much this is the same situation we are in today. There are a whole bunch of my colleagues, some of them use the word AI bros, who would like you to believe that we are on the path to human extinction, whatever, AGI, right? Grand, glorious future where we've got tools that are able to operate as humans do, with collective intelligence significantly beyond human capability. I'm not one of those guys. We are very practical people trying to build real products for real consumers now using these technologies. And in doing so, a year ago, what we presented was this point of view. Okay, if you have this mindset that you are a very practical person, an engineer trying to get stuff built, what has happened? What has changed with a GPT-4? And this is the slide that we put up. What has fundamentally changed is that we've got a new kind of computer available to us. It's the first generation of computers that you could think of as being designed for humans, in the sense that they are dealing with language somewhat in the way that humans do. And again, by language, I mean text, tables, documents, a whole bunch of sequenced media that we use to communicate with other humans and with computers. And the big change here is that instead of all the formal programming languages that we have worked on for decades, where you have to go formalize the real world in your head and then write down the code for doing certain manipulations on a representation that you designed. Instead of writing all the code for doing that in your computer, that's the old way of doing it. Those are the boxes that you see out there. We are now in a position to go a little bit meta, in a position now to talk with our new computers, these things that you see up there, via text. What kind of text and how? Well, okay, that's the big deal. And that's what we'll be spending a whole lot of time on. That brings enormous power and brings enormous challenges. So the big deal that has happened is, instead of just the old style computers, and instead of people being our only exemplars of entities, information processors that understand language, we now have these new hybrid creatures that behave a little bit like humans and a little bit like old computers, very much like old computers in the sense that scale. These things are able to work at a cycle that is much more consistent with this sort of cycle than that, and at a scale which is much more compatible with this than that, but they're able to process language which this could never do, and that does. So good, so we got a new computer now, and the whole goal is to figure out how we can use this computer to do stuff for us. Can you go to the next slide, please? In an interesting way. So this is the old 1.0, 2.0 way of looking at things for me. As I said, I've done a bunch of work in programming languages. That's my major area, in constraint programming and high performance computing and so on. For me, this is a big enough divide to say we have now entered a CS 2.0 regime. In the 1.0 regime, it was about what I said a minute ago. It's about figuring out how humans figure out how to represent a situation in the real world in a computer, and how to write the code when you know how to solve a problem. That's what you used to do in computer science. You had to have an algorithm, a representation, write the code, get it done. That's how we used to work. But now it's a little bit different. And now it's different primarily because what the heck do you do when you don't actually know how to write the code? And I mean here things like this obvious example from Fei-Fei Li and folks back in ImageNet a long time ago. Your goal is to take a picture and label it with a task with a simple word like people, child, house, and study. How the heck am I going to write the procedural code in the old way of doing business for such a problem? I don't even know the complexity of representing all the bits in this image. Some of them are important, some of them are not important. On what basis do I figure that out, et cetera, et cetera? So big challenge there. But what we do have available to us now is a lot of data, in this case, a lot of labeled data, which hopefully we can use using machine learning algorithms, we can use to train a new box, which effectively given as input, this sort of an image will come back out with a label of this following kind, even on unseen images that were not part of the training set. So that's the whole magic of machine learning. I do not have time to go into it in any detail, but what I will do is go to this slide to get quickly to the point of view of where do large language models, where do transformers come in? And they come in primarily because, well, so there's a whole sort of separate talk to give on what deep learning is about and what transformer architectures are about. But let me just quickly reprise for you what's happening with large language models is they're built on a specific kind of deep learning architecture, where what it turns out, what is really important here is that first of all, it's deep, meaning you have many, many layers, potentially hundreds of layers, and you have something called attention, which you can think of as a way of taking some input representations and figuring out from them a bias, a certain set of weights that depend upon the similarity of the input representations to each other. You're doing this in an attention level, one level. There are a whole bunch of multi-headed attention things going on at one level, and then you've got these stacked up very deep. Ultimately, what this is doing computationally for you is you're getting it, and this is all trained end to end on your data. You feed data in at the bottom. At the very top, you will get out whatever label it is that this whole system is being trained to generate. That label you compare with what is supposed to be the label because of your training data. And if it's not the same, you'll get a loss. You propagate that loss, you change the weights. This is how this whole system learns, very deep, stacked through these point-wise connections between ultimately the inputs as managed by these attention layers. And I'm saying something about attention because this will turn out to be quite critical for understanding this new framework for multi-shot learning, or what's in-context learning as is being exploited now with multi-shot stuff. And it turns out that attention has a crucial role to play. But in any case, whatever it is, think of it as you've got a big deep learning architecture. The input that you can provide to it is language, something like cat on the hot tin, and what you get out of it as the next thing coming out, as the thing that is coming out is what is a probability distribution on the tokens that can follow this. That's the causal language model self-supervision. I'm jumping through a whole lot of it because I assume now people have become really familiar with this stuff. I just want to lay the ground for where we are. And so what this is giving you is now a box that can input language and output language. So ultimately, from a computer science point of view, this is where we are focused. We've got a computing engine that we can send text to and that produces text and has been trained on massive amounts of data. What data? Text data that's available on the net. And there's certain other steps that are needed as well in order to actually make it so that it can follow instructions. In the input, you can say, please do this, this, and this. And it's actually doing something that is in terms of the processing that it does that is consistent with the instructions you just gave. So a whole bunch of extra steps that come about because of this. But the real question that you're faced with now is, okay, what kinds of inputs? I'm now programming this machine. My program is input text. What kinds of programs work? How complicated can my text be? How much extra input can I supply in my text to this program in order for it to do the task that I need to do? That is the central question in front of us, developing, so to speak, a programming methodology for LLM-based computers. Can you go on to the next slide? Thank you. All right. So over this last year, there's a whole bunch of new developments that have happened that are pushing forward our understanding of this space. So one of the most interesting directions that people have gone into is increasing the context size. So this text that you feed in is bounded. You can't feed in huge amounts of text. So it used to be that you could feed in maybe 4K tokens. Text gets chunked into things called, it gets tokenized, small tokens, roughly parts of words. Let's just think of them as words. So, maybe 4K words. Turns out a whole lot of things you want to do, 4K is not good enough. Okay, so people went to 32K, 128K. You can get GPT-4 with 128K tokens. That's a lot. You can accomplish a lot of stuff. But Gemini came out now with a 1 million token, and there are technical papers out there that are talking about how you can go significantly beyond 1 million. And that would be absolutely amazing to see essentially an unbounded input length. But that's been significant progress in the sense that there is now Gemini 1.5 Pro available to anyone in this room. You sign up, you pay a little amount of money, and now you can feed an LLM 1 million tokens. Just think about it. 1 million tokens is like many 100 pages worth of information in a single query that you're sending to your computer. That query can contain data, it can contain what you want it to do, and it comes back having processed that stuff. So significant more power because of this. Again, there's a whole lot of underlying technology and what makes that work. That's not appropriate for this thing, for this talk, so we're not going to go there. A major thing that is happening though is, so there are 3 things that really an LLM gives you. First, it gives you some built-in knowledge about the real world. That's incorporated in the weights that it has learned, billions of weights that it has learned, the values of which it has learned through its pre-training process. So it's knowledge of the real world in those weights. Second is facility with language. And that facility with language essentially comes about just because of that little function that we showed you. Predict the next token. Again, I'm talking mainly GPT here and GPT class, so-called decoder-only machines. There are other variants of these that we're not going to talk about. So for them, you're really just training this whole pre-training stuff step by just getting it to predict that next token, a probability distribution on the next tokens. So 3 things. 1, knowledge of the world. Second, great facility in working with language. And the third big thing is this, I think, there are very, very few people around, if any, who would say they were not surprised when they saw in-context learning. So in-context learning came, first real manifestation of it came about with GPT-3. And turns out what you can do is you can take a little prompt, ask it to do a certain thing, and provide some examples of your new, you may have just made up this task. And provided a few examples of the input for the task and the output for the task. A little bit like what you are setting up for a real machine learning run where you're trying to fine-tune an engine. So in my input to this computer, I'm providing a bunch of examples of input-output labeled pairs. That's it. And then I give it a new input pair and ask it to produce the answer. So I'm not training anything here. It's the weights in this GPT-4 or Gemini are going to remain absolutely unchanged, even after it has returned its answer to me. But what we see is that there are many, many, many patterns that we can express via our choice of input-output examples in text, in context. That's what it's called, in context. Many, many patterns that the system is able to figure out. Even patterns that we have no reason to believe it has ever seen before. And it can complete the example that we provide without that output. This is called in-context learning. It stunned everyone when it came out because nobody had an explanation for what the heck is going on. This thing, we've usually associated this improvement in behavior by providing a bunch of examples with some kind of machine learning going on. And machine learning was always stateful. There are a bunch of parameters. As a result of learning, you're changing the values of those parameters. They become different. And they have, so to speak, learned about the phenomena. And now you probe it with the new thing, you get an answer. Here, there is no state. And there is still learning going on. So it's a very surprising thing that has happened. A lot more progress now on understanding what it works. And most importantly, we now have with the Gemini, this possibility that those millions of tokens, you could use them for sending in 50,000 examples, 100,000 examples of a new problem that you are interested in that the system has never seen before. You may just have generated those. And there's a strong possibility that you will actually be able to get results on a new example that you give without having done any fine-tuning whatsoever. So look at it as a lazy man's or a lazy person's fine-tuning possibility. This now opens up with that progress in ICL, and I will present a bunch of data about this as we go. So that's a big thing that we will be spending time on in this talk today. There is a bunch of stuff about making fine-tuning far easier to do, quicker, cheaper. A way of making this completely vivid is that just last week, people came out, I think it was Hugging Face people, came out with, okay, we've got 310 new LLMs. And what they did was they took about 31 data sets, or 10 base LLMs, and used this LoRa-PEF technique to train those to get a new fine-tuned instances of the base LLMs on this data set, and they are able to do it. What this is really doing is performance efficient fine-tuning. It's really looking at, do we actually need these big 32-bit weights in order to capture the relevant information during machine learning? Turns out you often don't. You can reduce it to 4 bits, in some weird cases to 2 bits, and still get great performance. So that's what that whole area is about. And I think we're going to increasingly see more and more work that shows you do not need a 175 billion parameter model in order to gain real advantage of the sorts of things we are seeing. You are able to squeeze it down into smaller and smaller models. This we will cover as part of the ICL stuff. It's a question to ask. You've got this new computer. What can it do out of the box? Broadly, we already said what it can do. You can give text, it'll produce text. Okay, but let's talk hardcore computer science. What kind of computable functions does it know how to operate on out of the box? Turns out with the Gemini, for example, now it can, okay, let me ask you guys this. Do you think it can do sorting? Obviously, since I'm asking, you will say yes. Okay, sorting of 10 long lists, 100 long lists, 20 long lists, efficient, correctly. Let us say 90% or more accuracy. Any ideas? 1,000 long, 100,000 long? Okay, it's not that wild, but you can get sorting at the level of something like better than 50% accuracy for 200 long lists of numbers between, say, 1 to 100, not massive numbers. No, sir. The prompt is, I want you to sort this list. And here's the list, 100 long. And I'm not giving any multi-shot examples of sorting, right? So I'm relying on its internal knowledge of what sorting means. Turns out you can get great answers. There's, again, a whole bunch more of examples here. For example, linear classification, even nonlinear regression. Turns out of the box, an LLM, you give it a problem. Here, you would be using, for a regression problem, you'd be giving it examples of your instances of your regression problem, input and output, some number of those, complicated ones. And it's able, Gemini is what I've tried on. Others, the papers that we'll talk about, I've tried on Claude and GPT-4. These roughly I will call the GPT-4 class of computers or class of LLMs. It turns out you can actually get linear and nonlinear regression working very well, even a complicated function such as Boolean parity checking. How many XORs for a long sequence of Boolean? You're counting the number of these things that are one. Complicated function, you can get these guys to do.
Let me clarify what I
Please.
In a ChatGPT, I can ask ChatGPT generate the code for regression, and then I can ask ChatGPT to execute it.
No, sir, that is not what I'm saying.
That is not what right.
This
I
is
wanted
not
to
what
make
I'm
sure.
saying. Thank you. Thank you for asking. You can absolutely do those things. And ChatGPT, sorry, I haven't spent much time with ChatGPT. GPT-4 will do that. It will generate all kinds of complicated code. Last year, we showed it generating code for essentially a traveling salesman problem, right? That's beautiful and wonderful in its own right. Here I'm saying out of the box, I'm giving you the input-output pairs, some number of them, for a new function. I'm not even naming that function. I'm simply giving it a new input and saying, give me the output. And in the case of these parity functions and so on, you get, you're not getting 100%. You're not going to stop doing old computer science, but you're getting a very surprising performance of over 40% correct with this kind of in-context learning, whereas you try to use GPT-4 directly and ask it to do it, you're not going to get a lot of mileage. Okay, so there's a surprising amount of new stuff going on here to try to characterize this computer. What can we actually do with this? I'll ask you another question here that might hopefully get you thinking about it. I'm assuming you guys have worked with LLMs. Okay, what is the most complex, what is, I'd love to see from you an example of an input program, an input to an LLM, with, let us say, the output is to be bounded. It is still, not growing with n. It's bounded amount of output, but where your LLM is taking way more time than it has ever taken on other problems that you've tried. Okay. So what I'm trying to say is, if this is really computing functions, we know there are some functions that are very hard to compute. It takes a lot of time to compute. So I got bounded input, bounded output. I should still be able to get it to do some really huge amount of processing. So think about that. I have managed to get it to do, spend minutes, GPT-4, to come back with an answer, whereas for most queries, maybe it's going to be 10 seconds, but here it's minutes, it's still thinking about what's going on. So there's a lot of stuff to do here to understand how does this do its computation. Now, one of the major problems we face with using LLMs in practice is that we're going to produce a lot of text. So some people have said that Sam Altman killed email, because now with GPT-4, it's so easy to produce all sorts of spam email that your spam filters cannot catch. I think LLMs will kill documents. It's very easy now to get LLMs to produce professional documents that look and smell like real documents, but may not be real documents. So it's going to become very, very difficult in a professional setting like finance to understand how to earmark content that is actually human generated and different from machine generated content. And it's probably going to come back to being actually able to interactively work with your data set. That's going to be an important characteristic. But here, the thing that I'm pointing out is that if you're going to produce a lot of text, you need to know, if you're going to do this in production, you need to know that the text being produced is stuff that you can trust your investor, your portfolio manager to consume and go take actions in the real world based on that, and they're not going to get led astray. So it's a huge problem to figure out when is the setup that you have here, LLM, the input you gave it, when is it producing output that is, so to speak, not grounded in reality? So an important way to do that is to figure out how to, quote, fact check the output. There are a bunch of nice papers now that have worked this out to some extent. And the ultimate problem here is the output is natural language. You've got to now kind of do the reverse thing and go from text to what are the decontextualized facts in the text. So you can send them to something else, some other piece of code to go check whether those things are true or not. So that's a technical language problem, NLP problem, and there are good progress now on solving it. Again, there are pointers we can give you to all of this. Don't have time to do this. Self-discovery, I'm going to talk about. Let's leave it there. This is also a very big deal for us. Nico is going to talk about this. We're going to skip over this, but for finance, for modeling real-world phenomena, this is a very, very crucial thing to do. And we used to do things with causality extraction from text based on the old NLP stacks. And now there's far more powerful techniques available with LLMs to do it. So that's a big deal. We'll talk about GraphRag. This is the idea that if there is a query that you need to process with an LLM, again, it's the massive input size that is your friend. You may have a query that's just 2, 3, 4 sentences long, but now you've got a whole lot more input that you can give to it. So how do you augment this query with relevant information that's going to get better answers from the LLM than if you did not do that? That's retrieval augmented generation, generation being the thing that the LLM does at the end. So the whole game is, how do you retrieve properly to actually add value and not noise to it? So there are a bunch of ideas which are sort of obvious that have come out now. Microsoft guys have published here. I think, Nico, we are going to talk about this as well, where instead of thinking of all your resources, text resources available to you in the standard way of doing it is you take your text resources, you break them into chunks, you vectorize those chunks, you take your input, you vectorize it, now you find similar vectors and you add it to, get that text, add it to your input, send it to this darn guy. That's vanilla retrieval augmented generation. Doesn't help for a whole bunch of queries, does not work at all. You're trying to do comparative analysis. You're a financial guy and the earnings season has just come out and there's a whole bunch of earnings announcements, say in banking. You want to know, the question you're asking is, what is the trend across all of this? What are the major things that have appeared? Those trends, a simple way of explaining what is the problem with RAG is this. Someone else did it, it's not me. The question is not the answer. You are actually looking at this question and looking for stuff that is similar to it to find answers. Wrong. It may just not, the answer may have a completely different linguistic form than the question. So moving from the linguistic form of the question to that answer is a difficult, subtle problem. Graph RAG, where you actually go from that text representation to some more abstract knowledge graph style representation, where there's an explicit calling out of concepts, facts, relationships, so on and so forth, offers the opportunity where, given your input text, you go to some nodes in this graph, and then you pull the relevant things around that node. So you're now working not just at the level of text similarity, which is what vectors do, but you're working at the level of whatever knowledge extraction you had done, whatever view of the world you had explicitly extracted from all of this text, you're leveraging that directly. We will talk about this stuff. Okay, we've got this. I think, yep, so the rest of the boxes, Nico's saying time to move on. Thank you. Okay, this I've discussed, so let's go on. Excellent. Are you doing this, Nico? Am I?
I think you start with that.
Okay, I'll start and then you can get going. Okay, this is again a reprise of something we showed last year. What we showed was, all right, so you're going to now try, you've got a lot of text. And from this text, you want to extract facts according to some ontology. The old way of doing things is open-ended relation extraction, again, natural language, lot of techniques for doing it. None of them really worked very well. And one of the requirements for a number of those techniques is that you have a prior ontology, a prior set of concepts that you're interested in extracting. Here, we are trying to do it in a way where all we know, and the example we gave last year was, all I know is that I care about the earnings season, and I care about extracting knowledge from the earnings reports that are coming in. So the first thing I do is I ask my LLM, that's your task, to extract information about the real world structured for what might be of interest to a financial analyst from earnings reports. Please propose what is an ontology for this. And here we're doing something very similar. So again, you go one level indirect, you're trying to solve the problem, you pose the problem to the machine and see if it can solve that problem. So here's what we say. By the way, this is a running thing that we are doing. We did it last year, we're repeating it this year. You have to work with some sort of complicated real world domain in order to illustrate various ideas. I can't work in finance here because that's my private job. I can talk about movies and so on, and I will actually when I get a chance. But here what we picked up was New York City. You need to guide people who are coming to New York City for things that they can do. You need to design their schedule and so on. So now I want to get actually a knowledge graph out of this. So here's what I say. Please extract from the description given to you key terms, relationships, what you would expect. Here's meta information about what I'm looking for. It's not an ontology, it's like a pre-ontology. Give it this, and I tell it, hey, there's a knowledge graph I'm going to be adding stuff to. Again, I don't know if it's crucial that I tell it this. I don't know if it really knows something about knowledge graph. That's a whole different ballgame to go into about how we can systematically probe these LLMs to figure out what is it that they understand about various concepts like this. It's a different research topic to go on. So we tell it, okay, I'm going to, and you can emit JSON, you can emit data log, different. I think we're going to talk about emitting in relational AI as well. So we give it a schema for the kind of thing it must produce, and then we give it the event ID, and we give it the passage, and we ask it to produce stuff. Next slide, please. And this is the example of something that one of our colleagues actually extracted, went off and extracted from the Eventbrite. This is an example of a description. Let's go take a look at what that thing produced. Next slide, please. Yep. So you get this. Now, this isn't quite a knowledge graph in the usual sense, because most of the sort of values in this, I have, of course, identified here concepts like descriptions, activities, interests, location, and so on. But most of the content here is text, but it's not very difficult to break it down into also symbols instead of pieces of text. You have to do some named entity resolution to do that, but that's also pretty well understood. My bottom line here is simply to say it's as easy as this now to generate a knowledge graph, facts that populate a knowledge graph from just raw text. But a caveat, if I work in deep domains, complex domains, and it's not so easy to make this work in really complex domains, because there are subtleties of understanding the concepts that it is not at all clear that this machine knows out of the box, and you try to get it to answer questions, and you fail miserably. So I'll give you a simple example of this. There is, in the investment space, there is something, people, I'm talking about fundamental analysis, people will write things called, analysts will write an analysis of a particular ticker, from an investment point of view. So they will look at what are the headwinds that are faced, what are the tailwinds that are faced by this particular company. They're going to produce a page, maybe 5 pages of dense text that captures their view on what's going to happen. Obviously, it would be very valuable to check it for consistency. In other words, are they saying something in one place that contradicts what they're saying in another place? Now, another human can go sit down, look at all of this, and do it. Our challenge is to get LLMs to do it. For this notion, I'd call it a pretty sophisticated notion. I've tried to generate without using multi-shot training, so just 0 shot. Try to get this program to work in a way that would satisfy our professional users. Very, very difficult, not able to do it. The point is that this notion of consistency is very specific to a domain and is sort of deeply understood by professionals in that domain. There was no reason to believe that this LLM would actually trained on all the stuff on the net have actually captured that. But because we see amazing behavior elsewhere, we think it might. So we tried. Didn't work. So there are examples now of where a GPT-4, and I should have said before, LLMs, I mean GPT-4 class LLMs whenever I'm saying this, because you can get the open source LLMs and they are getting way better, but they're not quite at the level of capability of these things. So simple domains, you get some really good answers out of the box. And now, of course, the goal is to iterate. The big challenge is, if I use that query on one simple description, it'll come back with some choice of those predicates that you saw. Give it another one, it might come back with another one. So that's a problem, because now you've got to reconcile all of these names across all of these. So the obvious thing to do is run it once or a few times. You'll get a bunch of examples. Now you put those exemplars in. This is, again, the few in-context learning that I was talking about. And now you will find more or less the same attributes that you have identified in your initial examples are the ones that it is producing information for. So it's a very simple way to bootstrap it to get into a coherent ontology. And of course, you can add, if you see, you can curate that ontology. And you don't have to do it this way. You could get a human to look at it and add that stuff so you are able to get the system to do a better job. Next slide, please. Okay, now it's yours.
Yeah, that's myself. So I want to confess something that I realized that there was something wrong with the order of representation, and actually tried to edit through my phone. So I think I made it. Let's see.
Oh my God, I see.
Well, let's see if that works. Like, it's a special skill. Have you ever tried to edit a presentation on your phone? It's not the easiest thing, but you can do it.
But you didn't use an LLM, so you should be
No,
good.
I was the LLM. Anyway, so this is kind of like a small demo, if you want, of what Vijay described over here. You know, you've all heard about RAG, and everybody talks about graph RAG. So what I will attempt to do over here is crawl Wikipedia. We got about 100 bios, resumes, and actually 50, not 100. And we try to extract facts and then answer questions. This is kind of like the prompt. It took several iterations to come up with the prompt. It wasn't easy, but so far it works. And the idea is that, you know, Vijay, you talked before, you're trying to extract relations and entities, but you're also trying to make sure that you keep the redundancy low. You will always have redundancy, okay? So you will say somebody was employed or worked for, or, you know, did business with. It will never be, you know, the clean, nice ontology that probably this community 5 years ago was used to, that doesn't exist anymore. Like if we want to utilize LLMs and go wild, we have to use you know, ontologies that they're redundant. And here, for example, when we do the retrieval and say which university my friend Vijay has attended, it is trying to find out or the relevant ones. And here's kind of like the prompt. Oh, no, it's not the prompt here. Now, once we find them, we have to go, you don't know this language, it's still evolving. This is the language that we're using. And that's a nice thing that despite the fact that ChatGPT or GPT-4 hasn't really seen that language, which by the way, looks a lot like Datalog or functional declarative language, we were still able to create templates. We gave examples, what is the abstract question, what is a concrete question, and this is what you need to generate. And the ability to generalize has improved a lot. Here's kind of like the prompt that we used, and here's where we provide all the examples. What we realize is that it is fairly easy to structurally, you know, in a structured way, keep adding more and more examples. Think about them as instructions, okay? So this is the poor man's instruction tuning. We didn't have the infrastructure to go and fine-tune instruction tune a model, but we realized that you can go slowly and give examples, very carefully curated, and the system, you know, learns. And so this is more about, in some cases, it needs to synthesize, it needs to do conjunctions, disjunctions to do that. So this is actually, I don't want to bother you. You're going to get the slides, and if you want, you can look at that in detail. And then you generate the query, and then you pass it back to the LLM to give you the answer. So these are some questions. I just want to mention something, that these are questions that you could have potentially done with typical RAG. But the problem is that the problem with RAG is that it can never guarantee that it returns all the results. Okay, we'll find some documents that they have. So if you're looking for one answer, RAG most of the times will get it, as long as it doesn't have to jump around a lot. So, you know, which universities has Vijay attended? It generates the query. When did Steve Jobs die? That's probably one that, you know, typical RAG would have given you, or find all companies in the software industry. It wouldn't have been able to do that unless you were doing this careful extraction.
Just to be clear, that REL code was generated by GPT-4
Yes.
and then executed in REL and to get you that answer.
Yes. So this is a more complicated one, and it gets that, let's say, 95% right. So Vijay asked me, says, can you provide, because he's in the financial industry, and there is a lot of value in know your customer and money laundering, and you want to make sure that two people were never linked together. So say list all people who have collaborated in one way or another before. Now, collaborated in a business setting can be in several ways. So what happened over here, it did find relations like, you know, person employed at a company, or a person was a member of a company, or person was owner of a company, or person like was a founder of a company. But it doesn't do cross-check. So you can find if two people were founders, co-founders, if two people worked, but if I was the founder and Vijay was working over there, it needs to create more disjunctions over here to do that. Which we can teach it to do that. This is quite common, and it's still an unsolved problem. But the interesting thing is that the language model can basically enumerate all possible combinations of relations that you need, and then you can actually score them. And you can go back to the user and say, well, are you interested in this case or in this case? Or you can start learning which combinations are the relevant one. And if that starts to remind you of something, this is what probabilistic programming was trying to do for many years, okay? And I think we're getting closer to that through a completely different path. So you basically find all possible ways to answer a question, and then you score them. And if you want to be exhaustive, you are exhaustive. So let's see if we figure. So that's the tricky part right now with the this in context learning. I did like in context editing. So Vijay, let's see.
Thank you.
So take it from here.
Okay, thank you. You can go to the next slide, please. So I've already covered much of this material in abstract fashion. Now let's just go through some of the papers and talk about it. So as I said, from a computer science point of view, it's a very simple thing. You've got a new computing element. What the heck is going on? How does it work? Getting to a causal understanding of how a computing element works is critical to using it reliably in all sorts of contexts. So the first paper that from a theory point of view tried to illustrate what it might be the mechanism in context learning is this. So it depends. So this is from these folks at Stanford University, great authors here, by the way. It relies on the following intuition that, again, all we are doing is taking this deep attention-based network, feeding it text and asking to predict the next thing. So whatever computational phenomena we are seeing is ultimately going to come from that. We're talking about the pre-training step. So here the idea is that, hey, likely this deep layer of stack of attention layers is actually learning latent variables that correspond to some semantic representation at a document level. So at much larger context lengths, in order for it to be able to successfully predict that next token. And so the idea is that that machinery for figuring out some abstract representation of a pattern in long pieces of text, that machinery already exists in these attention-based LLMs. Now, what we are doing when we are giving it certain examples within a prompt is we are offering it examples that are quite out of the distribution from which the system was trained. Because trained on massive amounts of data, that distribution is roughly speaking the text on the net. And now we're talking of extremely specific examples for which you want to learn. So there's a clash between the distribution of the pre-training data and the distribution of the prompt. But the idea is that if in fact the system is able to find a pattern in these elements, that since it's already been trained to find patterns, if it can find a pattern in these elements, by the way, its ability to do this becomes much better when the example lengths are improving. And here, even examples without labels help. So in other words, you don't have the output label. You just have a whole bunch of input examples. That is allowing it to figure out the pattern using its machinery for these discovering document length patterns, and then applying it on this input example gets you the answer. They have a much nicer way of explaining all this than I have stumbled through in the last minute. And they have actually got a proof that this works in a specific context where they picked a very concrete model of document generation from a mixture of HMMs. And they showed that in that context, this is how this could work. So that's great. Let's go on. This was just 2 years ago. Here is a simple example that illustrates all this. Okay, we are asking in our query something like examples are Albert Einstein was German, Gandhi was Indian, Marie Curie was. The system is supposed to answer this. And so the idea is that in the data that this was trained on, possibly there's a whole lot of wiki data. So there's possibly a latent variable that corresponds to the fact that this piece of text that you are seeing is associated with wiki biographies. And in that context, a natural thing, as you see there, Albert Einstein, full name is provided, was a German, the nationality is provided. In that context, it makes sense that the LLM is able to pick out through that path what the answer should be. So this was a nice explanation for what could possibly be going on. Let's go on one more level. Here is, no, I think one more. This is slightly out of place. Yeah. So this is another paper that came out last year, where they go into a lot more depth from Microsoft people on what could be going on. And they make this very interesting analogy that this, and this is what I was talking about earlier, that attention is actually an important component of all of this. They're making the analogy between what the transformer attention mechanism does to weights is actually quite similar. They use the word dual. I'm very reluctant to use the word dual in this context, but their word is dual to what stochastic gradient descent does on weights. So in other words, there is something, remember, stochastic gradient descent is working in the backward direction. You send your stuff, your input through the network, you get an output, you compare it with the thing, generate a loss, send it back to update. That's what gradient descent does, is compute those gradients and find how things should be tweaked. Here we're talking the forward pass. ICL works purely in the forward pass. There is no backward pass. You're just executing, you just, right? So, so this is a interesting, not very obvious analogy that what attention is doing can mathematically be understood as what gradient descent does. And so essentially, the gradients that are generated by looking at these examples through attention work a little bit like in situ updates on weights when they are applied, meaning applied in context, not applied in terms of changing the underlying weights, but they're applied in the context of existing weights. That's how you get the behavior that you get with ICL. So their claim is that, hey, ICL is essentially implicit fine-tuning. Let's go on to the next slide, please. If you need to edit, that's okay. You can edit. I can move the slides. No. Now this is good. Thank you. No, please go ahead. Edit. This is okay. I can deal with it. So now that we have some idea of what this underlying mechanism is, and I mentioned this, so I'll quickly go over this here. There's a nice paper that just came out a couple of weeks ago that says, okay, can we get these LLMs using this machinery of sending input arguments in? Can we get it to do linear regression, nonlinear regression? And you're talking Claude 3, GPT-4. I've actually done this on Gemini, and the results are quite similar to Claude 3 results, so they're very good in comparison. So here what we are doing is, this is just an MX plus B example. In fact, there's another version where you've got noise also associated with it, and you are trying to get the system to actually predict what the value will be for a new element. In fact, I went one more and asked the Gemini to generate the formula, right? And for linear regression, it's not a problem. It tells you, here's the formula. Here's AX plus B plus noise and so on. This is a much more complicated nonlinear function where now you are seeing errors. These are all taken, I'm sorry about these things. These are all taken from a distribution. This is sampled from, where the numbers are between 0 and 100. Some are much smaller than that, X4 and X3. And so the errors here with Claude 3 are around 2, which are taken other machine learning other machine learning systems that are trained is not too bad. Again, the training here is all in context stuff. Let's go on to the next slide. Okay, so this is a paper I strongly recommend people to read. It again came out just about a month ago or so. And this goes into this notion of, we've got 1 million tokens. Let's use it for doing many shot learning. Let's go on to the next slide, please. And they show, here are examples. Before this, the sort of orthodoxy, it's hard to say orthodoxy because such a new area, but whatever. The common wisdom was that you don't want to give many shots, just 2, 3, 4 are enough. Turns out that's a mistake. That was a limitation of the GPT-4 machines that we were using. If you've got a machine that can actually take a lot, give it a lot. And you see here, 18% 18 points improvement going to 2048 shots for sentiment analysis compared to a 32 shot. So this paper doesn't provide a lot of theoretical analysis. They just give you a ton of examples to show that many shot is actually working. On next slide, please. And here's the result on the parity stuff. It's 40% performance, but compare it with random chance, that's like nowhere. Compare it with GPT-2 that was trained on about 20 times more data to get to 40%. And this is able to, with in-context examples of around, 8,000 examples, it's able to do better than what was trained with 20 times more data. Next slide, please. Linear classification, more examples of complicated functions here. The point is to show this red stuff is actually k nearest neighbors, KNN. So it's doing sort of like KNN at a large number, which is kind of stunning. Again, no explicit training for any of these KNN-like techniques within all we did was compute the next token for the sequence. Next, please. Just so, for me, it raises a very interesting problem where we have a ton of symbolic computing problems. Let's even say NP-hard problems. Can we get interesting behavior out of these LLMs on such problems? Because fundamentally, there's a school of thought that believes NP-hard problems, there are just a whole bunch, because we don't have a proof for NP hardness, so NP is not equal to P. So maybe there are just a huge number of patterns that are lying out there, which can actually solve these problems. So one way to test that would be to try to get LLMs, which are very, very good at very deep pattern matching, to work on, in fact, combinatorially hard problems. So here, this is what they tried. They've got some kind of a logistics thing. It's nowhere close to what state-of-the-art systems can do. But again, just few short examples, they're getting at somewhere around 30%, 38% success rates. Okay.
So I think I'll start this with a context learning, but we're doing self-discovery of that. So that's so if you remember last year, we talked about this, we tried this problem, call it the tourist in Manhattan, which I might actually try to make it a formal benchmark. So planning your holiday. So the plan is we have a tourist, is supposed to be, this is Gen AI here, a Greek tourist. He wants to spend a day in Manhattan. And, we want to check if the LLM can be a good reasoner. So we're going to see two ways of doing that. One is Vijay is leaving the room. Come back, it's you. It's with self-discovery.
All right, thank you so much. So go ahead.
I just wanted to say, so we'll try to see if it can be automatically done. And if not, how can we help it a little bit? So Vijay, take it.
Thank you. All right, so now we are back to programming. How do you program with these LLMs? Next slide, please. So the simple thing to do would be ask it to generate a schedule. And I think you have something. We have tried to do that. You don't get really good answers. So there's another lovely paper that just came out. This is, I think, I don't have the date on it, but it's within the last year or so. So there's a whole, now what you're doing, the game here is to discover linguistic representations for patterns of reasoning that you can use to trigger the LLM. Okay, LLM only takes language as input, so it's got to be linguistic representations. Now, again, it's learned some notion of how humans operate through the data that humans have produced, etc. So maybe we can leverage that to be much smarter about how these things do work. So a simple idea behind this is the so-called chain of thought prompting. So here you ask it to not just, this goes back when I was at Goldman a few years ago, there's a lot of interest in trying to get some kind of explanations out of language models. And when 2020, when I started working with GPT-3, it's like, We don't have to worry about this anymore. This thing that's going to generate an answer will generate an explanation of how it produced that answer. Now, it may not be good, or it may not be correct, because it could be unmoved in what it was actually doing. But at least you have another handle to get it to produce that. And now you can provide that as input and say, here's a template for the chain of reasoning that was done to solve a problem like this before. And so guide this into certain patterns of reasoning based on expressing more linguistically about how the solution is derived. So that is an example. And in fact, I think Cockley was involved in that chain of thought paper as well. This carries that out to a much deeper level. So go next slide, please. Okay, so here's the idea. The idea is that you've got one problem. Maybe this pattern of chain of thought reasoning isn't the right pattern. After all, we have many, many patterns as humans for solving complex problems. Why don't we get the LLM to figure out that pattern for this problem on its own? Now we are in the space of what I will talk about towards the end as well. We're in the space of getting LLMs to write the code for LLMs. Okay? So the whole trick is, how are you going to accomplish this? So here's what we're going to do at a broad level. We're going to tell the LLM, you have available to you a whole bunch of, we'll call them reasoning modules. It's like in the quotes, it's not really reasoning modules. Techniques for reasoning, whole bunch of them available. We ask the machine to figure out for this problem, which of these are relevant. And then we ask the machine to specialize the ones it has chosen to the context of this problem. And then we ask it to execute that. So roughly speaking, it's like, here's your problem. Here are all the tools available to you. Go generate something which will work well on this problem using whatever knowledge you've got inside. And then let's go through and see what you get. So let's go on next slide, please. Right. So what they showed was, in fact, this does much better than zero-shot chain of thought reasoning on a bunch of academic benchmarks around, math reasoning problems and the hard problems in a particular benchmarking example. So here, 67% is the method, is the result with self-discovery with Palm. And with GPT-4, it's at 81, whereas without using this technique, you would end up at 58. So there's a huge jump in a bunch of these, not so much in this example. Now let's see what this might mean for our, you've got to have a name for that wonderful looking tourist.
I never found a name, so
Yes.
be creative here. Think about one.
Spiros, he's one of your, yeah. Okay.
Spiros, okay.
Great. So we've got Spiros wanting to visit New York City with his family. And so our goal is to generate a schedule. So let's try to use self-discover to just frame a simple problem and see what the system comes up with. Next slide, please. Okay, here is the list. This is the color I use for input to the LLM. Here's the list that's from the paper. There were 36 reasoners. And you can see, try creative thinking, generate innovative out-of-the-box ideas. It's sort of almost, motherhood and apple pie. But it's useful to have a whole long list of these and give it to the system so that it can choose. Let's go next slide, please. So now this is a few steps. This is the prompt for the first step. Select the reasoner. Assistant to a problem solver, given a task description, that's here. You're given reasoning modules, that's here. And your job is to select some of these that will work here. Okay. And here's that's an example of the input to the task. So this is Spiros coming in, and the task is scheduled for a family of 4. This weekend, between 5 to 7 events, total cost under this, and should be convenient, distance minimization, start from the hotel. I don't know yet what that is. I'm giving a generic task description because I want to get a generic plan, not tied too much to the details of a particular family. Next slide, please. Okay, so having done that, you get some output. You feed that output back in here. This is a multi-staged thing. Again, I'm not using words like agents and agentic programming. A number of my AI bro colleagues do that. I'm just showing you what the underlying programming techniques are. You put a label like this is what agents are like, and you suddenly take it to a whole different space of science fiction where it's very hard to figure out what people want to see happen and what they're actually able to accomplish. So I'm just focused on what I'm able to accomplish here. So you bring that in, multi-step guy, you bring that in here, you give still the task to be solved, and now you ask it to rephrase the reasoning module carefully so it's better suited for this task. This is step 2 from their paper. I'm not doing anything interesting here, novel by myself. And finally, operationalize. You take that output, feed it in a next step. So I guess there is one basic meta point here to emphasize. You could say, why 3 steps, right? In the sort of old computer science 1.0, you define 3 procedures. Why can't I just inline all of this into one procedure and make one call? Doesn't work so well. Because there is some kind of behaviorally what we see, there's some kind of confusion when in one prompt, you want the LLM to do different things. It doesn't do as well as when you break it up, empirically, right? That's all. So that's why it's done in 3 steps. Let's go on to the next slide, please. Okay, this is what it came out with. I didn't show you those intermediate things, I don't have time. This is what it came out with. Spend a second to look at it. It's not bad at all as a generic plan for addressing scheduling problems in the context of visits to New York City. No, skip this. This is all of it. There's 4 steps. Sorry, back to previous slide. No, yeah. There are 4 steps, okay? And they are about gather detailed information, compile a comprehensive list of potential elements, transportation options, hotel location nearby, blah, blah. Then use a reasoning module 0, which is named in there, to generate a set of potential schedules, decide their feasibility, and then divide into subtasks and tackle each separate, so on and so forth. So it's a credible way of doing it. Let's go ahead, please. No, skip this. Right. So here's what I did. The plan looks great. Now I need to execute it. Turns out, I'll show you that in a minute, but here's the thing that I did that worked. So took that plan, that's the execution plan, took that task description. Here the task description includes specific stuff about the family, and ask it to give me just the list of events that are appropriate for this family for this weekend. I gave it only events from this weekend, so I didn't have to search a very large database. Came back with some pretty reasonable events. I don't have the details here on show you which ones these are, but let's go to the next slide. Now, what if we try to execute this directly? So what would we do? We'd have to write another prompt. That prompt is saying, okay, you're going to take the shortlisted events here as input, and now you describe all your constraints on what the schedule should look like. Events should be on the same day as the schedule. Why am I doing stupid stuff like this? It should know. Well, okay, try it. It doesn't know. So of course, it depends a whole lot on the level, the temperature at which you're doing this. I'm doing this with Gemini 1.5 Pro. I'm asking it to do a combinatorially hard problem to actually come out with a schedule. It turns out that all of this stuff that I'm saying, some of those constraints, it will faithfully execute. Others it will ignore. The next time I try, some other ones will be faithfully executed. Some other ones will be ignored. It becomes a nightmare to try to actually get this to work reliably for this problem. So let's do the next one. In here, so the one thing you need to understand about LLMs is that they will always produce an answer. It might be gibberish, but it's an answer. And if you're not careful, you can easily get lost in, on the surface, it looks great. So big recommendation, if ever you are in this position of using LLMs to produce stuff for complicated tasks, make sure you've got a massive number of constraints written out on the validity of the output that gets produced. And what I was doing here was to ask it to follow these constraints in generating it. It may not do a good job. So you need to externally check, validate, send that stuff back in. You could ask it to do that yourself. This is a very important technique tied to self-discovery, self-improvement technique, where, and this I first saw when I was experimenting with GPT-4. 3.5, the chat GPT that someone mentioned, didn't do this at all well. This is the idea that you take a program, you get an output, and you ask the same machine with a different program to check that output for correctness. And, pardon me? No, sir, no, sir. No, there's no learning going on. No weights are being changed. I am simply using another program, which actually I could be using Claude for this, or another LLM altogether, and saying to it, Here is the output. There, right there, what it says at the top. And so an AI system has produced a schedule. What I'm trying to communicate to it is that it may not be perfect. There may be problems here. So you, the system, need to fact check this and check these constraints against what has been produced and label the ones that are a problem here, right? And of course, you have to have an exit condition. So you've got to say, because you're going to put this in a loop, you've got to say that if there are none, if this is good, according to you, LLM, then say it's good and you can exit. You'll have an outer loop running. It's a little bit like the reinforcement learning setup in that there is an agent and there's a system outside that is running that agent, so to speak. It's like that. So, your remark wasn't completely off the wall here. So yes, so you run it here, you're going to keep running it. So you need an exit condition. So you get that here. And I will tell you this, for this example, I've not been able to get this to work well, but self-improvement has worked for us in many examples. I'll give you one concrete example where it worked. A colleague of mine, his job is to, one of his jobs was to write what is called a Fed speak system. In this great world of ours, there are a bunch of people known as Federal Reserve Board members. And they go out and give talks about what they think is happening to the economy. Interest rates will go up or go down, whatever. It turns out there's a real reason why they do this, because they're not allowed to talk to each other, except in that meeting. So they use the press to communicate with each other by making these statements. So now, of course, what it means is that we have access to what they are saying. So we could try to decipher what they're saying. So this is the Fed Speak project generally. A bunch of people have worked on it and have results out there. The challenge is, you don't want to just say the sentiment is positive or negative. That means nothing. You want to know what are the 40 underlying factors and what is the stance on each of those factors. 40, I'm just making it up, large number of factors, right? So that's the real problem. So you're going to now produce a report that has a whole ton of detailed information about what those factors are and what those numbers are. How do you know it's grounded in reality? Again, it's plausible, as we said, LLM's plausible result, of course. So what you want to do is you want to put in, and in our case, one of my analyst colleagues saw it and said, you know what, it is saying that there is no support for a stance on the labor market, and it follows that by 5 quotes. Not good. If a human looks at this, they're not going to trust this stuff. So the natural question to ask is, can I get another LLM program to look at the output of the first program and identify those statements that are inconsistent with each other? In this case, a very simple inconsistency. And we were able to get a prompt like this to work, not a problem. And when you work, what I mean is you have to be careful here. You don't want it to generate the entire new report because LLMs very expensive. You don't want them to produce a lot of text. You simply say, give me the number of that item. You number all of these, which is wrong. And so you get a very small output and then iterate and so on, got it to work. Okay, next slide, please. And then tied to that is repair. So once you've identified the defect, to iterate back to the reinforcement learning analogy, you actually need to repair the program that you had. You can ask the system to repair. Again, didn't work very well here, but this is the schema for repair. Roughly speaking, it's the same as the initial schema for generating the initial schedule, except that you now say, there are a bunch of defects, there is an initial solution, produce for me a new solution. Okay, thank you. Next.
Okay, so I'm gonna jump on what Vijay said. So I tried a simpler version of that problem, but I introduced that kind of verifier. Okay, so this repair process that Vijay introduced requires for you to go and catch the errors. Okay, and I think that's where the knowledge graphs are coming into place. So let's take a simpler program. It doesn't have to do with events. You want to visit at least one museum, visit an art gallery, maybe it's optional. One Greek restaurant, of course, he's a Greek tourist, and go to 2 bookstores, but you shouldn't visit the bookstores consecutively. There must be a break. And the total trip should be less than 2 miles. Okay, so I went to the LLM and I asked and I got a few sites. It's actually pretty accurate because I went and I verified the latitude and the longitude that it gives you for the all the landmarks are actually correct. The only thing that doesn't work well is DALL-E. Like the images, they have a lot of errors, by the way. Text works really well. but on the image generation, we're still a little bit behind. You see, there's a lot of typos and a lot of inconsistencies. So I use a much simpler prompt here. These are the constraints. It's a simple verbalization. And in the beginning, I gave it, the list of the museums with their coordinates. And then this time I didn't use rel. I said, I'm going to do it in Python. I wrote 9 functions that they basically take the result and they check if these constraints are correct, are satisfied. And if they are not, it gives back the error message, what's going wrong. You check the types, because sometimes it might present a restaurant as a museum. These things can happen. And then this is kind of like the repair that Vijay said. Well, you provided this plan. Here's the feedback, errors and messages. Start from what you have and go and change it. Now, it turns out it's a very bad idea to give numerical data to an LLM. Because
at
I
least
think
the current LLMs, at least today.
at least today, we don't know about tomorrow. And they can do addition, they can do multiplication, but it turns out that there are some references that it consume a lot of its resources. Okay, so if it's a trillion parameters, it uses a lot of its attention to try to make that right. So that didn't work well. The system wasn't working. It was producing a lot of junk. It was computing the distances, sometimes correct, sometimes wrong, and sometimes it was hallucinating. It was using the wrong coordinates. Now, I try to pre-compute all distances and give that as an input. As you understand, that's something that doesn't scale, and I exceeded the 120K prompt window. Besides, what I found very interesting is the pricing of Google. Computing 3200 distances was about $35, about 1,000 times more than the budget I had spent working on the GPT-4. But you can compute the nearest neighbor graph. So I used the Python to compute all the geodesic distances. That's kind of like cheap. And then, this is a proxy of the true Manhattan distance or the true walking distance. And I said, if it's less than a mile, then compute that. So what is important here, what you need to get is that using the relational information into the prompt as a background information, it's much better and much easier for the LLM to consume, other than giving numerical information. So just saying that these are the neighbors and this is the distance, because it can do this simple addition. Okay, I'm going from this restaurant to the other restaurant. It means I can add the distances and get an estimate of where things are. I only used 322 calls and I paid $3, still much more expensive what I paid for the GPT-4. Now, something interesting as I was playing with that is that for each distance I had to pay 1 cent. But you can actually ask the LLM and say, do not use Python to compute the distance, try to estimate it. And it came with a pretty good answer here when I asked it to compute the distances. Basically, it found out from the addresses how many blocks they are apart. So it kind of computed a rough estimate. And it was, here it says 2 to 2.5 miles. And the true distance is, 1.6. It's not that bad. Okay. And what is even surprising, can do for other cities. This is my house. Oh, now you got my address. Okay. Very secure. To the supermarket. And it says that they're the same code. It starts getting it. So it's a little bit off. Says it's about a mile. It's half a mile. And I was thinking, wouldn't it be a great idea if we're actually putting into the pre-training data the open maps, so it can start having an idea. But the way that you put the open maps is not with coordinates. You would put it as the graph, like the road graph. Now, it worked really well. So on the average, it works like, takes about 1.6 trials to give you a right trip. It takes about 13 seconds. Now, I did some benchmarking. What if I try to randomly generate a path, go from here to there? And I'm putting some effort, not just like, just give me 5 destinations. I just make sure that the destination of the one is the origin of the other. So it's a continuous path. So it takes about 500 trials until it finds something that satisfies the constraint. So we do know that it works much better than, randomization. Of course, that takes a minute because right now it's much faster to run a random path on my graph on my computer versus what ChatGPT is taking. But all these things are becoming better. If I was using Grok, maybe it would have been as fast. Now, what you don't see over here is, well, where's your graph database? Why don't you compute that with a graph query? Is that a valid question? Because there's one problem. I mean, you could, technically for this one, you could. And it's a small problem, it would work well. But it doesn't work for any constraint. And some of them, in many cases, if you're trying to find paths, it will actually, the query optimizer will have to generate it will have to brute force it. So it doesn't take long until your query optimizer basically comes into this, actually behaves worse than that. Because this one randomly will get faster, rather than your query optimizer will end up brute forcing all possible paths in order to give you an answer. So I think the knowledge graphs and the graph databases are excellent at verifying the constraints. They might give you an answer, but what you actually get out of the language model is that it gives you in constant time, okay? Modulo how many times you will have to repeat to satisfy the constraints. So this is the final trip. You can see all the satisfies the constraint. It's about 1.6 miles. The family is happy. Spiro is happy. So, I did try to solve it before Vijay tried the self-discovery with chain of thought that it failed. It was trying to generate code. It wasn't making sense. I did talk about a graph engine. We did talk about KGs, how good they are at expressing these constraints. And here I wrote them in Python. Now, once the constraints start become bigger, this idea of writing a function for every constraint makes it cumbersome. Plus, some of the constraints might actually include looking up a database or fact-checking things. Okay, so what if I say, do not go to a restaurant that Nico has also been there? So it will have to check some kind of transactions or history to see that this is satisfied. We're actually working right now on increasing the constraint complexity. Sorry, but let's go to another problem where we use the verifier to make it actually work. So this is a problem, and it's kind of interesting. We have a blog post. The day we created the presentation was the day that Daniel Kahneman passed away. So it actually came exactly the same day. We didn't know about that. We're working with this problem. So you thought about, about like thinking fast and slow. I'm running out of time. I'll just go quickly. So war, immediately, instinctively, you say peace. It's fast, but it's prone to error. And that's kind of like an example where I give you a problem, you get it wrong. You can start working it out on a symbolic reasoner on Python, and you actually get it right. Okay, and now I'm going to, this is a standard benchmark, the blocks world planning, where you start with some blocks in an initial configuration, and you have to end up in a final configuration. You have some valid actions and some constraints, and you have to generate the plan. I want to say that there's a lot of work that has been done over there, and people have published papers where they give the beginning and the end, and they're just checking if the plan is correct. We actually did something else. We had the verifier coming step after step, and if you do that, you increase your accuracy much better. So if you can correct the model in the process, it's much better than waiting for it to do everything and then say that it's wrong. So we have a demo. This is like a small Streamlit app that Giancarlo made. It kind of visualizes what's happening in every action. And there's some cases say, well, this action was invalid. That's what went wrong. And it keeps doing that until it generates a solution. So this is actually something that we're taking into more complicated problems like now, like supply chain. So we're looking for more difficult planning problems. And now I'm going to talk about another optimization problem, which is the famous diet problem, where the idea is that you're trying to make the perfect dish for you to eat and satisfy nutritional constraints. And as I was doing that, Vijay found this on LinkedIn. Apparently, GE is actually using the Google Cloud, and they see what you have in your fridge, and they tell you what to cook or what you can cook. Okay, and I saw that and I said, well, yeah, let's see if we can. I didn't think we could do that. It turns out you can do that. So this is the problem. This is your knowledge graph, and this is what you basically. This is how you would. This is a very common problem in optimization. If you ever take an optimization course, this is like a standard benchmark. Like this is one of the first exercises you do in linear programming. So that's what we describe over here. So in our language, you can actually run optimization problems in our knowledge graph. So you can code it as a graph query if you want, as a reasoning query, it's logic. And this is the problem. Mo created the equations, and then John Winston coded that. And if we had time, we'll show you. It's kind of like there's a natural one-to-one correspondence. So it does generate a dish, but the dish is disgusting. If you see them, the optimization problem doesn't really know the optimizer what it's. This is the knowledge that we have, but Gurobi doesn't know, and there's no way that you can go and encode which ingredients go with each other. This is combinatorially, very difficult. And yes, so we did take the results and we gave them to the language model and said, well, that's absolutely not a great dish. Try again. So what we do is this is the combination of combination of ingredients that it's invalid, and we go and we put it back as a constraint. Well, generate a solution, but not this one because it's disgusting. And we try with iterations, but as you can understand, we had 7,000 ingredients, take all possible permutations of 5 ingredients. It's going to take a lot of time and then your constraints will start growing exponentially, and you will never get a solution. So surprisingly, the language model can actually solve the problem on its own, and it was really impressive how it did it. So I didn't have much time, so I restricted myself to 100 ingredients, and I asked the simple constraints. The calorie has to be between 800 to 1200, the protein and the carbs, and it came up with some valid recipes. I'll show you some examples. This is how the prompt and okay. Now I did a trick over here. I made everything in integer, so I made the arithmetic easier for it. Okay. So it did satisfy, and it actually gave me the way to cook it. So it gives you the instructions how to cook the dish, and it makes sure that it actually here says, well, you told me 1200, but I went slightly off, so I'm not 1200. But then I asked it to retry, and I say, can you make sure that it complies with like the French cuisine? And it worked. But as you're going to see, when I asked for Hawaiian, the carbs went up. I noticed that I've given it a very low requirement of carbs. And I asked it to correct it. And it did correct it, actually. But then I asked it about something even more difficult. I said, I want you to use potatoes or pasta because I know they're high in carbs. And, it again went way and above. See something over here that it only used 50 grams. It could have given me like 1 gram of pasta to keep, but it knows that this is not really valid. And it tried a whole wheat pasta to keep it low. Okay, and I still say that you are, that's not what I want. And now it switches to potatoes. Okay, and actually it switches to sweet potatoes because they're lower in carbs. Now, my thoughts is that whenever you have to deal with an optimization problem that has a combinatorial number of constraints, you cannot follow the original path. You have to go with the distribution. And the language models, if there is something that they know they can model very well, it's the distribution. It's called a language model because it's a probabilistic model. People have been trying to model the probability of words being together and these words can represent a lot of other stuff. So, you know, there is a great way to actually combine traditional optimization and language models. And again, optimization is reasoning, and reasoning belongs to knowledge graphs. That's how all these things are connected. We're all getting into this universal platform where all these things have to be, you know, together. So just, you know, a couple of papers. So the question is, what's happening if we want more difficult constraints? The answer is, I don't know if you've seen that, the Lean Dojo is a way of doing interactive theorem proving, where basically you have, this is the verifier here, is a math prover, and here's the language model trying to generate different directions of proving a theorem, and Lean tells you if it's correct or not. And that's a paper from Meta where they basically, you know, train with a lot of synthetic data, and they teach the language model how to do combinatorial optimization, or let's say difficult optimization. This is not combinatorial, this is A star here. And so basically use your knowledge graph to simulate the problem, generate tons of data, fine tune your language model, and then use it as a constant time solver. Okay, so we have 1 minute. Vijay, you're going to wrap this up. These are the confessions of a Gen AI programmer. You know, we got Madonna confessions on the dance floor, confessions on.
Yeah. So this is the takeaway from my point of view today, a year later into this journey of really trying to use this for production quality code. It's amazing technology, but a complete bear to work with to try to get stuff in production. I think I've explained some of the challenges. Here are, you know, first of all, bunches of places where it works quite well. So we know those patterns, we can use them there, not a problem. And again, I'm talking GPT-4 class LLMs, but there are, just simple example, I spent the last 2 days trying to get the thing to work correctly on executing the plan for Spiro. I can tell you tons of details about how that did not go well. So the basic problem here is, let me just mention this, continuous programs. How do you debug when your program is a piece of text? You can add stuff to it, take away stuff, remove a semicolon, remove a colon, and you have a black box. You're getting no feedback other than, does it produce the final answer on whether you did the right thing or not? It's a bear to try to debug these systems. Let's go to the last slide. Well, there's a beginning of a methodology on how to successfully program in this space. As they say, you know, the proof is in the margins. So we can talk about this later. And I just mentioned, I hope people remember these folks, this is Newell and Simon. The GPS stuff that they did a long time ago, it's coming back. The general purpose solver, that's what we're doing. Symbols, connecting symbols, proving, doing things in the real world with connections of symbols now through LLMs. And just the last slide is simply a whole lot more to do. I did this at IBM Research, you know, about 10 years ago. A bunch of things are crossed out. I should cross them out, but there's so much still left to do outside. So much to do.
Thank you.
Sorry we took so long. I was hoping to have some questions, but maybe we'll just stay back, and if people have questions, they can talk.
50 seconds over time. Big thank you to Google Slides for letting me edit them online.